Okay, let me share my screen. Okay, what you can see is the finding of the optimum reactor size. So this is actually design still of reactors, but this time you already apply maxima minima principle. Okay, in here you are given 100 grams of R. So 100 gram moles of R to be produced hourly. So this is the hourly production of R from a feed consisting of a saturated solution of A having a concentration of 0.1 mole per liter in a mixed flow reactor. So the reaction is 1 mole of A forming 1 mole of R, and the rate law is first order with respect to A. So it's 0.2 per R C sub A. Now, the cost of reactant at the given concentration of 0.1 mole per liter is 50 cents. Okay, 50 cents per mole A. And the cost of reactor, including the installation, the auxiliary equipment, the instrumentation, the overhead expense, labor depreciation, all those costs incurred in operating the reactor is 0.01 cent per liter per hour. Okay, so these are the costs. Since it's optimum, so we have to consider this time in our design the cost. So these are the required information. What size or what reactor size, feed rate, and conversion should be used for optimum operations. And for letter B, what is the unit cost of R for these conditions if unreacted A is discarded? Okay, meaning it's not recycled to the system and then forms a mixture with a new stream of A to be converted to R. So what is unreacted is just discarded. Okay, I'd like you to take a screenshot of the problem. That way we can have a discussion in the way we should write our solution. So that's our problem. And screenshot of the questions. So these are the required information. Okay, so now we go to our board, our Jamboard. That way we can write the solution of this. I hope you can see already the Jamboard. And this is the 6th sample problem on this set of slides. So we will write our given information. Okay, so we'll start with the given information. I hope you have taken the screenshot of the problem. So let me start with Rexel. Can you give me a given information? Hamid, Rexel. Can you give me information that was stated in the problem?
CaO mass is equals to 0.1 moles per liter.
So in here, you're given a, what type of reactor is given, Rexel?
Mixed flow mass.
Okay, so if it's a mixed flow reactor, so we'll have here a mixed flow reactor. We have here, we have this one. So the initial concentration that you gave me is the concentration of A that is being fed to this reactor, and that's 0.1 mole per liter. Okay, another given information, Aina. What other information have you seen in the problem, Aina?
The 0.2 RMS, R sub R.
0.
0.2 mass, R.
0.2 per hour. Is that it? What is that? I think you missed something. What is that?
0.2 CA, miss.
Okay. So that's the rate law. So the rate law is in terms of the product R. So it's 0.2 C sub A. It's first order with respect to reactant A. So another given, Jericho, can you give me another information?
The reaction means
The reaction, and that's
for every 1 mole of A, we have 1 mole of product R.
okay. So we have it here. And then another one, John Albert Villarosa,
The cost of reactant, miss, ang SA 0.50 per mole A.
cost of reactant. So we'll define this as C prime react. So the cost of reactant C prime react is 50 cents. Okay, per mole of A. Okay, another given information, Patrick Tagle. Patrick, can you give
Ang ang dollar ang dollar sub MS is equals to $0.01 per R liter.
okay, that's actually if you were attentive or observative enough, so that's the cost of operation.
Kadali.
Okay, how we operate the mixed flow reactor. Okay, so we'll have here C prime M. Okay, the cost of operation of your mixed flow reactor is 0.01 per R per liter.
Liter miss.
Okay, that's it. What else can we add here? Can we add something here? John Vincent Millares. What additional information can we add here? John Vincent.
Ang 100 gram moles of R, miss.
What is that? If you're going to read the statement, what does it say? (100 moles per hour). What is that?
Flow rate, miss.
Sang ano?
Ang product, miss. Product flow rate.
It's the molar production, molar production of product R because it's mole per R. So we're going to write it here. The molar production of R, of product R. So 100 mole per hour. So the usual thing that we encounter is that the molar feed rate is in the form of the reactant. So you're provided with the molar feed rate of the reactant. Now, contrary to that, another scenario in here is that you're provided this time the molar production rate of your product R. Okay, so that's 100 mole per hour. What else? Can you add something here, Josh?
Wala naman, miss.
O ay na siya. Can you please read again the problem silently and check what is that very important information that once we neglect, if present, will really be very detrimental in our solution. Can you please check again the problem? Read the problem again. what is being fed to the reactor in the first place? 100, it says here 100-gram bowl of R are to be produced hourly from a feed consisting of a saturated solution of A in a
Ang
mixing
epsilon, miss.
ang
Ay,
epsilon.
sorry, miss.
Correct. That's very good. It's the epsilon. So in this case, your epsilon is what? Since you're given a solution, epsilon A is, if you're given liquid solutions,
Not zero, miss. Epsilon is not zero.
when is it not zero? When is it
Or zero.
automatically not when is it automatically not safe to assume that epsilon A is zero? When is that condition? When your reaction is,
Mixed flow.
when your reaction is not mixed flow, but rather when your reaction is epsilon A, it's not safe to assume that epsilon A is equal to zero if your reaction is gaseous. If it's gaseous, your epsilon A is not to be assumed as zero. You are to solve for it if it's gaseous. But automatically, you can set it to zero when the reaction is liquid in nature. So since the problem is talking about a solution, your epsilon A is equal to zero. Your epsilon A will only be not equal to zero when it is gaseous, when the reaction is constant pressure, or when specifically the problem mentions that it's a varying volume system. These are the three conditions when your epsilon is not equal to zero. But if after computation, based on the principles that were discussed to you, your answer is zero, then be it, even if it's gaseous, even if it's constant pressure, even if it's varying volume. But the thing is, class, you really have to determine epsilon A when the reaction is any of these three conditions. Automatically, epsilon A will be zero if your reaction is liquid in nature or you're provided with a solution. Automatically, epsilon A is equal to zero. So now we're going to write our required information. So we'll transfer here on the next slide. So what are our three required information? May I ask Johan, what are our three required information for letter A?
Reactor size, miss,
So
feed
that
rate, and
is what?
conversion.
How do we represent reactor size?
Reactor size, miss, for miss, for optimal operations.
Oh, okay. So it's reactor size. But in terms of a variable, in terms of a representation, how would you write it? Because if it's just reactor size and you won't be able to identify its representation in the formula, how will you know that it's the one that you're going to, in the first place, calculate? So what is the reactor size? What is it that you're computing when you are asked for the reactor size? Reactor size is what?
Ang diameter, miss, ng reactor.
Reactor size is the volume of the reactor. Okay? Now, what about flow rate? Is that flow rate? Reactor size, and then you are asked for the feed rate, and then the conversion. Feed rate, how will we write feed rate? Johan, how do we write feed rate?
ng ano, miss, ang letter M na may dots na ba, miss?
Feed rate. In kinetics, we write the feed rate as this. Okay, the volumetric flow rate, that's the feed rate. Okay, conversion is of course X sub A. Okay, letter B. Now, letter B, what are we asking letter B? Okay, what are we asking letter B? Via
Unit cost of R, miss. Hello?
cost in producing R, right? The unit cost of
Yes, miss.
Okay. Now, since this is an optimization problem class, you will set up an equation in terms of the total cost. The total cost in operating your mixed flow reactor. And since this is an hourly operation, and for us not to have the unit per hour in all of our terms, we'll have a basis. So we'll have basis of 1 hour operation. Okay, we'll have a basis of 1 hour operation, and after that, you have to set up your total cost of production. So let's say total cost, total daily cost, that is, because we have here 1 hour, hourly operation rather, not daily. Total cost per hour, because I use the basis here of 1 hour, is equal to, so we'll have the cost of operation plus the cost of the reactant that you're using. Okay, so let's say we will represent this as total cost, the C sub T. The cost of operation is C sub M. And the cost of reactant is C sub react. Okay, it doesn't have the prime because it's the unit cost that I have represented a while ago with the prime. So let's go back to our given. So I represented the cost of the reactant as C prime react, and at the cost of operating the mixed flow reactor as C prime sub M. Okay, so this time I wrote here the cost of operation is C sub M, the cost of the reactant is C sub react, and the total cost, hourly cost, that is C sub T. Now, based on the cost of operating the reactor, so I'd like to go back to the given. Based on the cost of operating the reactor, this is it, including labor, maintenance, and all those things, you have 0.01 per hour per liter. And since if you notice the basis that we use is per hour of operation, then our unit for each of the terms in here, in our equation, should be per hour. It should be per hour because we have a basis of 1 hour operation. So for us to get rid of the per liter unit in here, in your cost of operation, then it follows that the total hourly cost for operating your mixed flow reactor would be your C prime M times the volume. What am I doing? I'm thinking of eliminating the per liter here and leaving only the per hour unit. So the cost per hour, that is. So since it's already based on per hour operation, then our unit here now per term would just be simply the cost, the money, that in this case it's in dollars. Do you follow? Now we go to the second. So the cost of the reactor, no, the reactant rather. So the cost of the reactant, we have this one here, the C prime react. The cost of the reactant has the unit 0.50 or 0.50 per mole of A. And as such, it needs to be multiplied with the mole of A and the mole of A will be taken from the molar feed rate. Okay, this is mole per hour already, the unit of this one. So you will have C prime react times the molar flow rate of A. Now, I'd like you to ask question in here in the equation that we have set up. That way, if there are things that are not clear, we can go back. So we simply came up with the things to multiply here per term based on the units that were given to us of the costing. So since this is per mole of A and I want this per mole eliminated, I need to multiply it with the molar flow rate of A. And since this is per hour, so this must be then having a unit of money per hour. And since we have a basis of 1 hour operation, then these are all having units referring to the first and the second term of dollars. Now, do you have any question here? Okay, I think there's none. So that's our first equation. So we need first to think of what are the things that we know already and things that we don't. So in the case of the volume, do we know the volume of the reactor? Okay. I asked you a while ago to give out the information that was stated in the problem and there's no volume. So then we need to find volume of the reactor, the same as the volume of the system inside the reactor because we have a constant density system. I'll go to the next slide. If you are to determine the V here, what equation do you need to set up? Or in what particular equation will you take it from? Jillian, I need the V. Can you suggest to me a formula or an equation that I can use? That way I can solve for the V. The V that should be placed in here because we know already these costs. A formula for the V. Where do I get the formula for the V, Jillian? You can help out, Jillian. Where will I get the V, the volume? Performance equation. Thank you, John Albert. Very good. You are to get the volume from the performance equation. So the performance equation of your MFR. So for our MFR, we know that tau is equal to CAO XA over the rate. Okay, this one is B over B sub O equal to CAO XA over the rate. The V that I want here, B is equal to CAO small v sub O XA over the rate. This one, the CAO v sub O is FAO XA over the rate law. Now, in this case, I'd like to write the rate law. So our rate law is in terms of R. So that would be 0.2 C sub A. Now, is there a problem with me using this one? Remember your rate law is based on R and it's 0.2 C sub A. Now, in terms of stoichiometry, so in terms of stoichiometry, you have A forming R. And as such, the rate in terms of R over 1 is just the rate in terms of A over 1. So it's just okay to write 0.2 C sub A in here, although I'm looking for R sub A. And what the problem gave is R sub R. Okay, so this is the volume. Now, what do I know here, and what is it still that I need to find in here in the right side for me to be able to find the volume? You don't know FaOXA, you don't know Ca, but you can write. So I'll write again here FaOXA all over 0.2, and I have CaO 1 minus Xa. Okay, now it's better. I have CaO and I have 1 minus Xa here. Now, what else? Do I know everything in this formula, or I will just simply express whatever I have here in the formula in terms of conversion? Do I know conversion? No. You don't know conversion. Do you know V sub O? If you have in mind to rewrite this into CaO, V sub O, that way you can cancel the CaO. But your problem is V sub O is also unknown. So it means, class, that in this case, the volume expression will be in terms of Xa. Because you don't know all of the three that are related. I'm referring to the size, the feed rate, and the conversion. They're all related, are somehow written in this particular equation. And what you can keep only as the unknown, or V expressed in terms of one unknown, is just the conversion. So we will do that. We will express the volume in terms of conversion. Now, in this case, now your problem is, if you will express the volume in terms of conversion, you have CaO already, it's given. Then this must be kept, the Xa. What about the FaOXA? Where do I get it? So if we go back to the problem, class, the problem gave you the product, the molar production of the product per hour, the rate of production of R per hour. And that's it. I properly stated it. So in that case, we can write, but F sub R is equal to 100 mole per hour. And we know that this F sub R is actually F sub RO 1 plus X sub R. If expanded, this would be FRO plus FRO XR. Okay, why did I have to write it this way? Why do I need to write it this way? Because I'd like to cancel out the FRO here, because initially there was no mention of product R present. So meaning we don't have an initial concentration of R. So in here, we could say that whatever is produced, it is coming from the A that was consumed. Okay, this FROXR is actually the amount produced coming from the consumed A, or the moles of A reacted. Now, why I need to write it in this manner? I'll first write this as equation 2 so we can go back to this later. It's because if we will continue in the next slide, your F sub R then is equal to F sub RO X sub R. In terms of stoichiometry, class, if you can write CaO XA over 1 equal to CRO XR over 1, that could also be translated in terms of molar feed rates. So you can write this as FaOXA over 1, and you have here F sub O XR over 1. Conclusion, FaOXA is just FROXR, which is just equal to F sub R. So from 2, this is your equation 2 here, we can change the FaOXA Your V now can be written as F sub R, because FAOXA here is FROXR, which is also F sub R. I hope you get it. And you have 0.2 CaO, 1 minus XA. And if we will substitute the given, so F sub R is 100 and CaO is 0.1. So we can place it here. So you have 100 over 0.2 times 0.1 times 1 minus XA. So I have now volume, you can write here volume, equal to 100 divided by 0.2 divided by 0.1 is 5,000. 1 minus XA. So a volume in terms of conversion. So I'd like to write this as equation 3. Okay. So if we go back to our first equation, this we know it's given, this we know it's given. Now we know this already. Okay. Now what about FAO? The last thing that you're going to write in here, the FAO. So we go back to what we have set up in here, this one. So we'll have FAO is equal to, from here, remember this one is F sub R. FROXR is F sub R. So FAO is equal to F sub R over XA. You transfer XA here, and this FROX sub R is F sub R. So this is equation. Okay, let's first substitute if there are values that we can place in here. So your F sub R is known to be, so I'll place here FAO is equal to 100 divided by XA. So this is equation 4. F sub R, 100 over XA. Now you have a V in terms of XA, you have an FAO in terms of XA. So we substitute 3 and 4 to equation 1. Okay, so we have now FAO known. So substituting to equation 1, so substitute 3 and 4 to equation 1, we have the total cost would be equal to, so the thing that we see here is C sub M, it's 0.01. And the V would be 5,000 over 1 minus XA. So you have 0.01 times 5,000, 1 minus XA. So this is your C prime sub M, this is your V in terms of conversion. Okay, we go to the next term. The next term that we have in 1 is C prime react, which is the cost of the reactant, which is 0.50. So we'll have here 0.50. We multiply it with 100, the F sub R, our equation 4 over XA. Now this equation can be solved using or can be processed using differentiation. Using maxima and minima, at optimum condition, we maximize conversion. So as such, in this case, you need to differentiate the total cost with respect to conversion. Okay, so if you do that, in this case, if you will have this differentiated, you will have 0.01 times 5,000, that would be 50. And you use power rule for this one, that would be -1. 1 minus xa raised to negative 2, and then you have the derivative of that, which is negative 1. For this, if you multiply, you will have 50, and you'd have negative 1 xa raised to negative 2. Okay, can you follow? Now, maxima, minima tells us that at maximum or minimum condition, the derivative will be set to 0. So setting this to 0, you will have, in this case, 50 over 1 minus xa, and this one minus 50 over x sub a squared. Okay, so we will have a value of xa. What's the value of xa? At maximum conversion of, is this 50? Okay, 50% we minimize the cost. That is why it's optimum. Is it 0.61? Can you please check? Oh, sorry. This should be squared. I'm miscopying this one. Now, you will get rid of the x sub a squared. So you will be left only with x sub a. It's 50. 50%, correct. So 50%. So for your letter A, so I place here, we're solving for the answers for letter A, the V sub O, and the X sub A. We already determined the X sub A. This is already one answer. This is the optimum condition. Now, once we already have the XA, the others will just, of course, follow. So if we go to the next slide to solve for V, so you will have V. We go back to the V formula, and that V formula is equation 3. Is 1, 5,000 over 1 minus XA. So you have 5,000 over 1 minus 0.5. So your V at optimum condition is 10,000 liters. Okay, one unknown, one more. The other unknown that we need to find is the small v sub O. Okay, what formula will I use for the small v sub O? How do I solve for v sub O? Remember, your FAO is equal to CAO small v sub O. In here, a while ago, our FAO is here, 100 over XA. So I'll have here 100 over XA, which is 0.5, is equal to 0.1. 0.1 for CAO. Yes, 0.1. V sub O here. So you now have the small v sub O. So it's 2,000 liters per hour. Okay. So we have this now as our feed rate. Okay, so we have answered letter E. Now we go to letter B. The cost of producing R. Check. the cost of producing R. So what's the cost of producing R? How do you compute for the cost of producing R? Of course, you first need to determine the total cost. So you go back to our equation 1. So our total cost is equal to the cost of operating the reactor. We're going na lang to the simplified equation. The simplified equation is this one. Okay? Equation 2. Do we have another one? Oh, we don't have. So if we substitute for this one in here, equation 2, FAOXA is the 100 point over 0.2 CAO. So this is 100 over 0.2 times 0.1 times 1 minus 0.5. Okay, where am I getting this? I'm getting it in here in our equation 2. This is 100, this is 0.2, this is 0.1, this is 1 minus 0.5. Now that's the V. You need to multiply it with the cost, which is C sub M. C sub M prime, which is 0.01. Because what I have there is just the V. So this is to be multiplied to 0.01. For the second term here, in the total cost, equation 2, this is equation 2. So I'll go back to equation 1. This one, C prime of the reactant is 0.5 multiplied to FAO. 0.5 and your FAO, which is 100 over 0.5 as well. 100 over XA, which is 0.5. So your total cost is 200 per hour. This is the total cost of producing R. How do you solve for the unit cost? The cost per unit, how would you solve for it? This is 200 per hour. What's the unit cost? How do you determine the cost of production of producing 1 unit? Or shall we say, how do you compute for the unit cost of R? That would be is the total cost divided by how much R do you produce per hour. So that would be F sub R. So your total cost, which is 200, if this is 200 per hour, we divide it by the amount produced per hour. I think this is the 100 mole per hour. This one. So this is 100. Specifically, your unit here is this is mole R per hour. So your hour unit per hour unit for each cancels each other, and you will have the unit cost of R to be $2 per mole R. So $2 per mole of R. If you go back to the question, if you're wondering why we need to solve for this, we go back to the problem itself. I'll share the problem again. Okay, what is the unit cost of R for these conditions if unreacted A is discarded? So, like to go back to our Jamboard, the unit cost of R. So, if in the required information, it was written the cost of producing R, what I mean here is just this one. But if it's the unit cost, then we'll have to change this specifically. Unit cost of R. Because if it's the cost of producing R, this would be the C sub T. The unit cost of R. So that's the reason why we have this as our answer for letter B. Though you don't get this one until you determine first the cost of producing R per hour. And since we already have the per hour basis, so this is now the unit cost of 1 mole of R. Okay? Do you have any questions here? There's none? Okay. So I'll go back to our slide. And that's how we apply optimization to reactor design in its simplest way, only to illustrate the principles. Okay? Now, the last part of this slide is just a comparison on how to distinguish the holding time, or the T with the bar, and the space time. The holding time is often used for batch system. So this is the mean residence time inside your reactor of your volume, of the process volume of your system. Okay, most often it's for a liquid system. So referred to as the time of reaction for a batch system. The space-time, we have already defined this based on continuous flow system. So this is the time required to process one reactor volume of feed measured at specified conditions and associated with flow system. Now, if the holding time and the space-time is the same, we have to think of when will this be possible. So this is possible if our system is a constant density system. So these two, you can use interchangeably. You can use the tau or you can use the T with the bar at the same time because your system is constant density system. And this is in the case when epsilon A is equal to 0. So it's constant density system. Okay? Now, again, there is a reiteration here of the definition of the tau and the space-time and the space velocity. Okay? In here, you have the tau, the space-time, and the formula, and you have here the residence time based on the formula for the batch reactor. Actually, what you have here is the performance equation for a batch reactor. Now, at the latter part of the slide, you have the summary of formulas which was taken out also from our main reference book, which is that of Octave Levenspiel. Okay, so this ends the very simple discussion on reactor design for single reactors and single reaction systems. Do you have any questions?
Miss.
Yes. I'll stop sharing. No. No question.